I'd like to leave as much time as possible for your presentation, so let's go ahead and get started. Just a brief message to the audience. We are currently recording this presentation, just as an FYI. Without further ado, it is my pleasure to introduce Dr. Pooyan Jamshidi, Assistant Professor in the Department of Computer Science and Engineering at the Molinaroli College of Engineering and Computing here at the University of South Carolina. Before joining USC in 2018, he held postdoctoral appointments at Carnegie Mellon University and Imperial College London, and he earned his PhD in computer science from Dublin City University. His research focuses on artificial intelligence and machine learning, with particular interest in causal AI, deep learning, trustworthy AI, machine learning for systems, and robot learning. His work combines theoretical foundations with impactful real-world applications in areas such as robotics, healthcare, neuroscience, computer systems, and space exploration, and he has collaborated extensively with industry partners, including Google and NASA. Please join me in welcoming Dr. Jamshidi.
Everybody, I hope you are doing well. I'm so happy to be here talking about some recent research, which is about AI systems at a scale. And this is also, I'm teaching a course, it's called Machine Learning Systems, which I go into the technical background of how we can build real AI system, such as Google scale. So, a useful AI system is not just a model, but also it is about the infrastructure that we use to serve these models. So when we build a system, we may have multiple models with different capabilities. Also, it requires a serving systems to serve such models. And there might be different components at different part of the pipeline doing different tasks, and there may be also a human in the loop that require to intervene at some point. So for this audience, the main question is not about which model variant is best, but it is about system level design decision, which system is useful, reliable, and affordable for serving the data and constraints that we have for the system. So I start off with reviewing some of the takeaway. Hopefully by the end of this presentation, audience learn something new. So it is first takeaway is about AI performance. It's not about the model as I mentioned. It's about what scaling decisions, specifically across the stack, including the infrastructure. And in scientific workflow, useful AI also should satisfy some constraint in terms of end-to-end latency, budget for the system deployment, minimum quality, which is related to accuracy of the system, also human oversight. And modern applications, as I mentioned, consist of multiple components that this creates an end-to-end pipeline, and there might be different trade-off about those qualities like latency and other metrics that are involved in such systems. And the key research questions is about how should we adapt the system when workload of the system changes, when we might have different data difficulty and different priorities that may change over time. So I start the talk by giving you some motivations, and then I go into the core principles behind this research. And we look at three systems ideas. For each, we have different publications that I will mention. Also, at the end, I include some implications of this research. Even though the research that I'm presenting today is technical and system level, But I tried in this presentation to keep it relevant for the audience in this talk, those who are doing biology, health, and public health workflow. Um, so about the motivation, why it matters beyond what we do in computer science, and it is actually a real world and very applicable to biology. For example, we have a system called digital pathology, which trials many images, and you have so many like images at a scale, so you want to do this task very quickly. Or maybe spend more compute on cases which are more difficult to do the task. Also, we have other type of systems of different nature, such as clinical or public health text-based systems that it primarily summarizes large volumes of notes, messages, report images, and also it requires a limited turnaround time. And in scientific workflow, such as uh, pipeline that start with some pre-processes of some images, and then detecting a specific cases, as well as classifying these cases, and there might be at the end some human review involved. And typically in these three type of systems that I mentioned, we have real world constraints. We have limited number of GPUs or CPU nodes or cloud budget in order to deploy and serve such systems at a scale. So we have these constraints, real world constraints that we have to deal with. And a useful AI is basically the system that make right quality decision at the right time, and the cost is also should be affordable and actual to the workflow. Also, we have common systems questions, which means that how do we spend limited compute in order to improve such pipelines at the scale? And by the way, if you have any questions, you can stop me. I'm happy to answer these questions. In order to clarify this further, so modern AI systems are increasingly composed of these different components that are weaved together in order to automate a task. And the core challenge is balancing the objectives, like such as accuracy, cost, and latency. And we have some uncertainty involved, such as dynamic workload and resource constraint that needs to be accommodated. For example, in digital pathology pipeline that I mentioned, you have a pipeline a stage which basically does some image pre-processing. And then it does some screening, and maybe some metrics are measured, such as uncertainty, which this metric may determine whether we want to use a larger model in order to reduce this uncertainty and increase accuracy of the prediction, or escalate it to human pathologists in order to look at it, because the uncertainty cannot be reduced further. And this routing to a smaller model or larger model or human is based on like maybe some constraints such as a threshold about uncertainty. So for example, in this case, when we change this threshold, make it lower, obviously it increases the number of escalation, which result in more cost and sometimes higher sensitivity. And on the other hand, if we increase this threshold, we have fewer escalation, we have lower cost, but we might have greater risk of missing hard cases. And the best threshold depends on workload. For example, how many images are involved and consequences of error. What if we make an error, and what would be the consequences of it? And also the available review capacity that are involved in the system at a scale. And the hidden layer is actually is a layer that decide where speed, cost, and reliability have to be traded off with each other by tweaking the system components. For example, we need to decide what model variant we should use for a specific images that comes to the pipeline. Um, should we batch these requests or send them one by one? How much hardware we should spin up in order to serve such models? And also, when should the system escalate to human reviewer? So these are questions that has to be determined automatically for such systems and determine a trade-off that we have in the objective space, which is about the speed, cost, and reliability. The question is that what happens when we run the system? First of all, like these model variants has to be decided. By model variants specifically, here I mean model of different sizes. And you know that larger model have higher accuracy, but on the other hand, imply higher cost for the system. On the other hand, small model are less accurate, but very quick and very resource efficient on the other hand. It may also we require need to batch requests in order to increase the throughput or spread these work tasks across different machines. And also about how many cores we should have inside each machine that serve the system. And in order to make users happy, we typically have a service level of agreement. So think about the constraint that we have about end-to-end execution time of the pipeline. So for example, if it takes for ChatGPT to answer your question 10 minutes, would you use it? Obviously not. And behind systems such as ChatGPT, there are evolved large-scale infrastructure that has to be optimized in order to serve such system at a scale. And you know that every person in the world probably using such system now. So the system is making many decisions behind the scene in order to provide such a low latency so many users at scale can use and find it useful. In order to make it very clear, what do we mean by this trade-off space? First of all, such pipelines, such system has to be highly responsive and also cost efficient. And by cost here, I mean the cost of infrastructure in the hardware side of things that is costly. And in order to serve the system, you have to pay for such cost. Also, you require it to be highly accurate. So accuracy also matters. And these objectives actually are conflicting with each other. It means that if we want to have higher accuracy, probably we need to pay a higher cost as a result, or having a higher end-to-end latency. And we need to find a right trade-off in a sweet spot on the objective space in order to make the system usable. On the other hand, we know that the workload that coming to the system is changing, is dynamic, could be bursty, meaning that in the morning, probably many of us quickly start using ChatGPT, and actually in the morning, like the OpenAI required to use more hardware resources as a result. So, but overnight, probably less users are active. So we have these patterns or fluctuating workloads that the system, as a result, requires to be intelligent enough in order to satisfy end-to-end latency and make it useful for the users. So the insights that I will share in this talk, um, you can find the details in these three publications. And these three publications are interrelated somehow. You can think about it as kind of a problem that we were able to formalize it in a multi-objective optimizations given some known constraints under some uncertainty. And we mathematically formulated that um, in order to come up with a solid solution uh, that help us to determine the right trade-off for the system. Um, a little bit detail about queuing intuition. So I mentioned that the workload changes. This means that the arrival rate for the system, arrival rate here, I mean the number of requests that hit the system um, is changing. So we have these arrival rate parameters. Also, we have the option to batch request and improve GPU efficiency. If we imagine if we batch several requests together, um, as a result of this, many operations can be done in parallel. And as a result, it makes the hardware resources more efficient or more utilized in order to serve the system. And for such pipeline, average latency across all requests actually is not relevant. Tail latency is important, which means that the latency when the workload is surging. You can see on the graph that for the period between 600 and 1100, there has been a surge in the workload, and the autoscaler, so the decision that was made by the system actually resulted in uh, violating the P99 latency as a result, which this means that the system for this period may not be that usable if it increases the end-to-end latency. Um, so So there is a trade-off between the workload, resource utilization, and end-to-end latency, as you see here, as a result of increasing of the waiting time. But it is also important to know that the scaling, meaning that adjusting the number of cores, like increasing the hardware size, is not enough. It helps, but it wouldn't result in an optimal trade-off in the space based on these results that we already have. First of all, larger model can increase accuracy, but result in a reduction in the throughput of the system. More capacity helps, but we need to spread it, use it for larger model, and this decision has to be made case by case, request by request, whether this request is hard enough to route it to larger model or is very easy and can be answered by small models. So a static deployment actually wastes resources, meaning that you are not utilizing the resources that you're paying for. because, for example, these requests are easy, so you could answer them with the small models. Um, so static deployment is not good enough, and you need to adjust these resources as the system workload is changing. So, more specifically, as I mentioned earlier, modern AI is a pipeline, meaning that it has different components to do pre-processing, to do detection, to classify the cases and summarize and escalate it to human review. And end-to-end latency is some of each stages on the pipeline plus the waiting between the stages. Um, and actually, like realistically, in such pipeline, there could be bottlenecks, meaning that some of these stages actually create the bottleneck and increase, as a result, increase the end-to-end latency. And actually, removing this bottleneck, performance bottlenecks, actually is one of the hardest tasks. Is actually a NP hard problem in order to do that because these components, these different stages interact with each other. So it doesn't mean that if you remove the bottleneck from classify a stage, you remove the whole bottleneck for the pipeline. It may move simply to detection, right, or summarization. If you don't do these decisions about model variants and hardware sizes properly for the pipeline. So the first insight as a result of our empirical observation uh, was that we could have different uh, model size, model variants that serve different type of cases. For example, we might have smaller models, we might have larger models, and we could route these different cases to different size of a model. For example, we can send harder cases, harder requests to larger models. And this routing policy depends both on the data difficulty as well as the current load to the system. And we know that the workload changes, and this routing policy has to be dynamic at runtime. So this insight was behind InfAdapter, the first publications on the list, that we find out that actually keeping alive these different model variants can help us to adapt the system over time. So each variant occupies provided different trade-off between speed and accuracy. So we have more granular trade-off space in order to find a better trade-off as a result. And the adaptive policy can move the system to a better operating point, meaning that it could have improvement in terms of end-to-end accuracy as a result of this decision. And a useful question is actually not about what size of model we use, but which one for which request we use at each moment, right? And this subset of models could vary over time as the workload of the system changes. And the second insight from this research was that the local decision can be globally suboptimal, and actually we need to make these infrastructure decisions, these systems decisions, jointly, not for each stages of the pipeline. So deciding independently for configuration for each stages actually would result in a like suboptimal end-to-end latency or end-to-end throughput. And the kind of changes that we can tweak the system are involved choices of what model to choose, what batch sizes, and what are the resource allocation for the system. And each of these decisions actually they cannot be made independently, and they interact with each other. So they have to be optimized jointly. And that's why we define a joint uh, multi-objective optimization problem and try to solve that optimization problem in order to derive the optimal decision. And local bottleneck, as I mentioned, dominate this global trade-off space between latency and cost, and different application might have different priorities as a result. So we find out that same pipeline can have different optimal policies. For example, we might have a pipeline that accuracy is prioritized, meaning that we want to spend more compute where making error is expensive, meaning that we don't want to make many errors. And that makes it accuracy prioritized. We might have a balance between these two, or we might have a resource prioritized, meaning that we only have very limited resources or we have limited budget for the cost of resources, and we don't mind losing accuracy in some cases where it doesn't matter. So we might have a resource prioritized policy as a result, and you can see some of the result that we have in terms of trade-off space. On the left axis, you see the number of cores that translate to the cost of the pipeline. And on the right, you see accuracy that is annotated in this plot for different pipelines. So on the x-axis, we have different pipeline from video processing to audio processing and some text-based pipelines such as summarization and NLP pipelines. So these are real-world pipelines that we use in evaluation. And the key lesson is to define the objective before tuning the system. Uh, and that definition of objective has to be translated into the multi-objective optimization problem that I mentioned earlier. And the third insight is about batching, which showed that batching can help, but deadline matters. So, and sometimes we may need to reorder the request in order to satisfy the end-to-end latency of the system. For example, in this case, batching increases the throughput. As you know, as I mentioned earlier, when you batch different requests, you can parallelize operations at the hardware level. So as a result, throughput would increase. But this doesn't mean that it doesn't have any consequences on the other objectives, such as latency. So we know that batching increases the waiting time, and that may also increases the end-to-end latency. And in cases where we violated SLA, the system needs to adjust the batch sizes or use more resources on the other hand. So good batching serves the GPU without breaking the deadline, but the size of the batch actually has to be determined dynamically based on the external workload. And this would also be translated in this type of systems that you guys are more familiar with in biology, healthcare. And first of all, this means that you have to define the pipeline, the workflow first, meaning that by workflow, meaning that these important stages that are independent from each other, such as the screening, triage, and down the line analysis, exploratory analysis. So these workflow has to be defined, and for each workflow, we might have different components and implementation. that sits on different hardware, right? So for example, for a screening system, we may put the screening component in one hardware, but the analysis in some other hardware as a result. Also, we need to measure the right metrics for the objective space in order to find the right trade-off. And this involves latency, cost per request, specificity and sensitivity of the pipeline, and so on. Also, we need to keep the human in the loop where errors are expensive or labels are noisy, and actually the cost of making any mistake could be high as well. Also, we need to benchmark the whole workflow, not only one model in isolation, because of the interactions between different stages, in order to make the system more useful. And here are some checklists for such scientific workflow, meaning that we have to answer these questions. What is the acceptable latency for the system? What is the minimum quality that must be guaranteed? What is the budget per request or hardware in order to serve the system? And which use cases, which requests should be escalated for human review? And where is the bottleneck in the pipeline and how we need to remove it? I would summarize some of the research opportunity that you can think about it that might be relevant to your interest. Would be happy to talk about any of these research opportunities if you are interested in. First of all, research on the direction of resource-aware AI serving on a shared hardware environment, and actually involving more interesting objectives such as, for example, the carbon cost of these hardware resources that we use for the system. Also, research in the direction of pipeline level evaluation in terms of usefulness, turnaround time, and accuracy. Also, human in the loop policies that determine whether to route it to human or use a larger model. These also might be interesting to look at, specifically in the context of health systems. And also adaptive multimodal pipelines where involve imaging, text, and other type of public health data. Also, as I mentioned, I'm teaching a course that interconnect theory, systems, and domain-specific concepts for AI systems at a scale. So to end this talk, I would like to summarize the 4 key takeaways hopefully you have from this talk. First is AI serving is a system problem, and decisions such as how the models should be routed or batched or use a larger hardware for serving such request has to be determined, and that is important. Also, we have real-world constraints in terms of latency, budget, minimum quality, and model applications are not only one component, but they are involved multiple stages that they are doing different tasks, and they may use different type of models. And adaptation is the key idea behind this work, that instead of using the same amount of hardware resources all the time, that may result in a wastage of hardware resources that could have been used differently, or may result in a violation of service level agreement. Instead, we adapt these hardware resources on the fly while the system is serving the request. Thank you. I look forward to your questions.
Thank you so much for that great talk, Dr. Jamshidi. We'll now open the floor to any questions. Feel free to unmute, or you can type your questions in the chat and I can read them out loud as well.
Uh, Question, if that's okay.
Uh,
Pooyan, great to see you
Great to see you.
here. Wonderful talk. Yeah, just so many things that I've never thought about in this space. So interesting. It seems like um, collaborating with people on how to design a system for a particularly difficult computational problem would be extremely difficult.
It is,
Um,
yeah.
yeah, to get them to think about these things. So I was just curious, what is that like? How do you go about that to start talking about these things?
Yeah, very good question. So typically, like, is involved designing, first of all, designing the system, designing the pipeline, figuring out how many stages the system we require to automate in the system. And these stages could have totally different nature. We may need to use a classifier in one stage to classify some images, and in some other components, we may need to, summarize the text. In another component, we may need to detect a case inside the image or interrelate an image with a text message, right, that we have in health reports. So we have a different variety of different tasks that have different nature. So this would translate into different, like, operations at the system and hardware level. You know that all of these machine learning tasks would be translated into some, like, matrix to matrix operations, right? And these matrix to matrix operations would be directly mapped to some very low level operations, mathematical operation that is actually deployed on the hardware resources. And, like, uh, the after figuring out the pipeline design, like, the important decisions is how to deploy the system. What resources do we have access to, and how we want to utilize these resources of as they change, as we observe the changes in the workload. And we are talking about, like, real deployed workload, not the type of system that we, like, program on or deploy on our laptop, kind of systems at Google scale, or at, like, also a startup scale, like doing some of the biology tasks, for example, that they might have, like, many users. Hopefully
Yeah.
it answers the question.
Yeah, no, it's very interesting, and I was curious, when you design these systems, do you use any type of any type of reinforcement learning to try to learn sort of adaptive optimal policies that will change as it goes on?
Beautifully said. Yeah. RL actually is one of the promising algorithm to actually figure out the optimal policy, uh, finding the solution to the multi-objective problem that I mentioned earlier. Uh, in this work that I mentioned, IPA, we actually did not do RL. Instead, we choose to do integer programming in order to solve, and we use Groby solver to find a solution for the optimization problem we formulated. But actually, in the course that I'm teaching, machine learning systems, one of the is uh, a student required to define their project and, like, implement a reliable system. And one group actually came up with a RL-based solution, which to find the optimal policy. And actually, that was really good and is a very promising approach in order to, you know, because it is best for finding these policies, right? Um,
Yeah. I have one more question. I don't know if Jaja, if you wanted to pop in here, but I mean, these, as you said, these really sound like really big systems. Um, so I'm trying to, you said, some of these are on like the scale of Google or a startup. I mean, or can you talk about some of the smaller systems that you've worked on and
sure.
just to try to give like me and Jaja like a sense of kind of what kind of scale those are on and
Sure. I
maybe
mean,
some.
like there are so many smaller systems. Um, imagine I develop a mobile app to, classify the type of flower that I'm seeing outdoor, right? So
Gotcha.
you train a model, you build a simple app that has an interface that talks with the model server that you have this model that you train. Obviously, like you may choose to train a large model that like you use large amount of data to train the model to be accurate and classify many flowers. You, but the size of the model may get large and like you may have constraint on your mobile in order to deploy such model, right? And this is
Sure.
like realistic. And like you may
Gotcha.
also release
Yeah.
this app and maybe like 1,000 user start using it, So you like there exists like a small and actually some of the students in my class developed such system. For example, last year a team developed a chatbot system that helped a student, USC student, to find the right resources instead of like referring to USC website or like a chat bot system that was um, using also a large language model at the back end in order to find these resources, which was and was used by like few USC students. So like we can have and define and design and implement such system at a smaller scale. But like uh, but it is this type of system are different from like imagine in a day I have a small task that I can automate and like only use my laptop in order to, deploy it and do the task, right? So that's different.
Gotcha. Gotcha. Okay. Thanks. That's all I have.
Thank you for amazing question.
Thank you, Pooyan, to give the talk in our INBRE. So yeah, so very nice. And I just follow up the Alex question. You know that we have actually collaborative project with Prisma, like implement the small system as what you mentioned. So for the voice suppression prediction. But
Okay.
so I would like to see from your point. So because put the things in the health system always be challenging. So what kind of the challenging you think when you design the app and how can you incorporate in the different health system? The other is that unique in the health system, or you actually see some similar difficulty in other system when you implement your small or big one?
Yeah. May I ask like what the system looks like, this type of system, Prisma system? Like
So I think the Prisma system uses Epic. So they have Epic system, but so the idea for us, I think in the original proposal is just to try to plug in a kind of the plug-in app, and then so it can just pop up directly. But so for the
and for such app, like I presume you might have model doing inference tasks. So
right.
and there could be different for this app, also the app that I mentioned with Flower, like you can actually deploy the model itself instead of on the mobile, you deploy it on the cloud, and on the mobile, you have just an interface, but it has to route the request all the way to cloud. So this could be a design decision. What are the trade-off space? This means that, first of all, like in order to do the task, the mobile user should have internet access. You know that. Also, it requires a network traffic all the way to cloud and sending response back to the user. Also, there are privacy issues. On the other hand, if you put the model in the mobile, obviously the user and each user has its own model that could be retrained. Like there are not privacy issue because everything stays on the user's mobile. Also, there is no network latency for requests. But on the other hand, what it does is that like you use resources of the mobile to store the model and also compute resources on the mobile to do this computation on device. And like these systems decision actually are real world, like for many for most of the AI-based app that we use on the mobile, for example, like ChatGPT itself, for example, obviously the model is not sitting on my mobile, right? So the model itself is somewhere in the cloud, and like the request would be sent to the cloud, right? But we have some app that actually the model itself sitting inside the mobile, right? So these are kind of decisions that has to be made at the system level, and typically it's not like randomly made or like ad hocly made, like, and typically the adaptation also matters, right? As user requests would vary over time.
Thank you. Yeah.
Thank you.
All right, any other questions? Feel free to type in the chat again.
I will also share the slides if you need to for the audience.
I was wondering if you could maybe go a little more into some of the practical challenges of deploying these in real systems, deploying these methods. Yeah.
Practical challenges. Yeah. So practical challenges typically are involve the decisions, the system decisions that has to be automated. For example, like when we deploy a system in cloud, we know that like for every virtual machine or hardware resources or service that you acquire from cloud, such as Amazon Cloud or Microsoft Cloud or Google Cloud, you pay for this, right? You pay for the resources, right? But on the other hand, you can like change these resources. Like for example, today you could use one virtual machine, tomorrow could be 10, and so on, right? Depending on the use cases and the amount of compute that you need. So determining how much hardware you need, typically like if it is automated and if this automation is based on some reasoning that result in optimal allocation of hardware resources, that's a very big challenge, right? It involves actually solving a multi-object optimization, which is costly to solve, and coming up with better algorithm in order to solve the optimization problem is a big challenge. So it involves both practical challenge, practical intervention, as well as like scientific exploration in order to solve the problem. But also like in addition to this, some reconfiguration. For example, I mentioned for some systems that are network that they have network communication. Some imagine some user may have low bandwidth, and their request may have been sent earlier but received by the system later because of this limited bandwidth. So this means that we may need to, so we find out that if we reorder this request and find the right reordering policy, this would result in a less violation of service level agreement, those constraints that I mentioned, instead of just keeping the order as they arrive. So basically, having a better batching policy there would help. And figuring out the right configuration for the batching also is an NP-hard problem, right? So these decisions obviously can be made ad hoc, but we may end up paying for resources that we didn't need, or we may end up with having a not usable system because it's so slow, right? On the other hand, if we adjust this like dynamically on the fly, that would result in a like better trade-off of cost as well as accuracy and usability of the system. That is like a key things. And these decisions again like are typically would be translated into NP-hard problem, but there exist solutions that actually like these type of I mean I mentioned that I collaborated with Google and like and with is this type of like systems actually is implemented at a scale in such companies or for systems at internet scales. So these are like practical. These are not only research based, and that's why I'm excited about this line of work. Yeah,
Awesome. Thank you so much.
thank you.
Any other questions from the audience?
One quick question. How often do you have this seminar series? Is it weekly?
So
Go
each
ahead,
semester
Joseph.
we have 4.
4, okay.
Yes.
And you
And
haven't yet?
Pooyan, so I have one. So I just mean when I jumped in, I saw one of your slides. I just curious. I'm not quite sure whether and my understanding is correct. You have one slide for the cost. Actually, the video one, you have low cost and high accuracy. And the sound, you actually have higher cost and high accuracy. The low accuracy. So I just because for me, video actually is more complicated than the sound. So I don't know. So is that because the video actually, yeah.
This one, right? So can you say which one you are referring to? Video has lower
Yeah, so
cost?
I think a video is more complicated than the audio. So this is why I just mean I'm not quite sure why it is low cost and high accuracy. But for audio, it will be low accuracy, high cost.
Yeah, good catch, good catch. But these are like, as you see, you're right. So, but voice processing also is not like typically you can imagine you would translate voice into an image, a spectrogram that would be analyzed by models, right? That's how ML models would predict what is inside the voice by like is actually the task itself would be translated into convolutional type of models and inference. But like also the cost and end-to-end latency is a byproduct of the type of data that we use as well. So the type of data in the audio might have been larger compared with the size of the images that we had because for each of these pipeline, we had a different benchmark, right? And
Yes.
inside each benchmark, there are different data sizes, right? But yeah, typically when we have like video processing, image processing, these are very expensive compared with some other modalities. But even here, you see that NLP has the highest ones, right?
Yes.
Which is text-based. But essentially, like across pipeline, the comparison is not meaningful. But within each pipeline, we have the comparison between different like policies, right? Whether it is
Yeah.
source prioritized or accuracy prioritized. But across pipeline, since we have different benchmarks, like
You didn't scale. Yes.
yeah,
Right.
their comparison may not be relevant much.
Thank you.
Thank you. And you can find the detail. And by the way, like all the code data, everything that we use in this line of work is on GitHub, and the result was replicated by third party, and also it's like on GitHub student can use it, can start replicating it, and maybe build some new idea on top of this framework that we developed. I strongly encourage students if they want to do research in this line of work.
Well, if there are any other questions, I would like to thank you, Dr. Jamshidi, for giving a great presentation. And thank you to the audience members for coming to join our seminar today. Yeah, thank you so much.
It was nice talking to you. Have a great day.
Likewise. Have a
Bye.
good one, everyone.